Donc, bonjour à toutes et à tous. Bienvenue à cette session d'échange que nous sommes très, très heureux d'organiser aujourd'hui. On parlera d'ESCO. On essaiera de reparcourir un peu l'historique d'un plan de gestion qui s'est fait dans l'ESCO qui est très ambitieux. Et nous avons ici deux intervenants. Tom Harris, qui est un chercheur en écologie à l'université d'Anvers, et Joris Vanlede, j'espère de l'avoir dit correctement, Joris, qui est un chercheur en modélisation hydrodynamique au Flanders Hydraulics et qui ont joué quelque part un rôle assez important dans la définition dans la mise en place de certains projets qui se sont menés dans les Flandres, justement, dans l'ESCO, et que je souhaite vraiment remercier puisqu'ils se sont impliqués et ils ont répondu positif à cette sollicitation, avec un effort d'adaptation quand même assez important pour venir à la rencontre de nos besoins. L'idée de cet échange, il y a quelqu'un qui m'a dit qu'il n'a plus de son. Est-ce que tout le monde m'entend? Oui? OK. Albert, je te laisse gérer ça. L'idée de cette rencontre, elle est née l'année passée, en fait, en 2024, quand avec Mathieu, nous nous sommes rendus sur leur terrain de jeu, l'ESCO, pour visiter un peu des projets qu'ils avaient faits. On avait trouvé les échanges avec Tom et Joris très, très enrichissants et surtout très inspirants. Et donc, l'idée qu'on avait eue, c'était d'essayer de les transposer, de vous faire profiter aussi de leur retour d'expérience et d'organiser un peu ce moment d'échange. C'est un moment d'échange qui se veut de toute façon libre, mais surtout dans lequel on souhaiterait aborder quelque part des problématiques communes que nous avons avec l'ESCO. Notamment, nous sommes dans un estuaire qui est, pour plein de côtés, très similaire au nôtre, à l'estuaire de la Seine, dans lequel il y a des énormes enjeux de conservation, des énormes enjeux liés aux usages, la navigation et des énormes enjeux liés au risque inondation. Ce sont tous des mots qui, quelque part, résonnent, comme vous le savez très bien, hein, dans les discours et dans les réflexions que nous avons actuellement en cours pour l'estuaire de Seine. Et notamment, peut-être que Joris et Tom auront des retours de temps à nous faire, surtout quant aux stratégies et comment mettre en place ces stratégies qui, pour nous, sont très d'actualité actuellement. Donc, il y aura deux présentations, mais qui sont une présentation unique, hein, si on veut, qu'on pourra peut-être dans lesquelles il y aura différents temps d'échange. Tom, il commencera, il ouvrira la session avec les grands enjeux écologiques de l'ESCO, quelque part, comment il nous retracera un peu l'historique des stratégies qui ont été mises en place là-bas, quels étaient les enjeux de départ, quels étaient les objectifs de ces plans de gestion, comment ils ont été définis et comment ont été mis en place, notamment dans le cadre du Sigma Plan, que c'est le plan qui s'occupe un peu de gérer cette partie de l'ESCO. Et Joris, après, prendra la suite pour aborder un peu toutes les questions liées à la sécurité, la prévention d'inondation et les projets justement de zone d'expansion des eaux sur lesquels il a travaillé. J'espère que donc cette première rencontre, ça sera une belle opportunité d'échange en tout cas, de croiser un peu nos regards, d'inspirer peut-être nos démarches. Donc, je vous prie de vous sentir totalement libre d'intervenir. Les intervenants sont d'accord pour qu'on puisse soulever la main au fur et à mesure que les questions nous viendront. Et ils essaieront de répondre en français, même si la présentation se déroulera en anglais. C'est pour ça que ce matin, je vais vous envoyer un petit manuel une petite guide sur comment activer la traduction automatique. Donc, n'hésitez pas à poser vos questions, soit en soulevant la main, soit dans le chat. Il y a Mathieu ici qui jouera le rôle de modérateur. Donc, encore merci pour votre présence. Je laisse la parole à Tom et Joris. Je vous souhaite une bonne réunion à tous.
Merci, Manuel. Alors, je vais présenter en anglais, mais j'espère de répondre à vos questions peut-être en français. Je vais maintenant partager l'écran. Et voilà, normalement, vous voyez mes diapos. Alors, l'estuaire de l'Escaut, so the Schelde estuary, I will start with a general introduction, and then I will tell about the nature restoration plan, while Joris is going to focus on the hydrodynamics. So just a short introduction. This is a map of the Schelde estuary, where the mouth is in the Netherlands, and I'm going to talk about the Belgian part, so the part in Flanders, where the estuary is. And it's a pretty large estuary with the saltwater part in the Netherlands, the brackish water part at the border, and then in Flanders, we have the freshwater part. And as in many estuaries, there was an increased risk for floodings, and there was a major flooding in 1953, a flooding mainly in the Netherlands, where more than 1,000 people died. And so this gave rise in the Netherlands to the Dutch Delta Plan. But in Belgium, the results of this flooding, well, it was limited. There were nearly no casualties. So in Belgium, nearly nothing happened. In the Netherlands, they started the Delta Plan. In Belgium, we just waited. And we waited until 1976. Then there was again a storm surge that hit the estuary. No floodings in the Netherlands. The dikes had already been raised due to the Delta Plan. But in Flanders, we had floodings. We had floodings in a village called Ruisbroek, more than 100 kilometers from the mouth. And so that was a sign for Belgium to also start with a protection plan. And that plan was called the Sigma Plan. This Sigma Plan of 1977 was just focusing on safety. So no nature was involved yet. And it consisted of 3 pillars. The first one was heightening of dikes. Then the second one was building flood control areas, 13 in total. And a flood control area, here you can see one of these flood control areas from the first Sigma Plan of 1977. It's Tielrode Broek, and it just functions as a large storage basin, and during a storm, water can overflow a dike and fill this area. And then the final element of this original Sigma Plan was a barrier, a huge barrier with pillars up to 125 meters. If you compare that to our cathedral, it was a huge project, and it costed a lot of money. And because of this, it was never realized because of budget cuts. The final piece of the Sigma Plan, this barrier, was not constructed. And in 2005, the government realized that an update was necessary. The plan was not finalized yet, but there were 2 things. There were, first of all, changing boundary conditions. There were stronger tidal conditions compared to 1977 when the Sigma Plan was initiated, and there was climate change. And then secondly, there was a new vision on integrated water management. So now aspects like sustainability, combining functions, ecosystem services, and building with nature or nature-based solutions were taken into account. And so from 2005 onwards, we are working now on a revised, updated Sigma Plan, looking at both safety and nature restoration. And the reason for that was not just because our government likes nature, but we did a cost-benefit analysis, looking at possible scenarios, and the scenario looking at more nature-based solutions was just the cheapest scenario. In this small table, you see the option with a barrier. So that's the original Sigma Plan, constructing a barrier. The second option was not building the barrier, but raising dikes to achieve the same level of safety. And the third option was building more flood control areas. FCA stands for flood control area, in combination with raising some dikes. And these 3 scenarios, they want to achieve the same level of safety. But it is clear that the scenario with nature-based solutions is by far the cheapest solution, so giving the biggest return on investment. So that's the reason why this option was chosen. And if we even go further with that, a flood control area, but it's a site that you use to store water to take away pressure from levees, but that side in there, you can do nature restoration. And if you do that, doing nature restoration in a flood control area, then you have a flood control area with a controlled reduced tide, FCA CRT, and I will show it later in this presentation. But if you do so, and you then start looking at ecosystem services, ecosystem functions, then you see that the benefits become even bigger. Okay, you lose some agriculture and forestry in that scenario, but you have a lot of ecosystem benefits, making the return period, making the payback time a lot shorter. And so the net benefit is the largest when you have more flood control areas with nature in them. So I also give this lecture to international students. And then the question is, well, then can we copy the Schelde Sigma plan to other estuaries? And then I have to say, no, because the Sigma plan is really tailor-made for the Schelde, specifically for the Schelde situation. And the solutions we have here are not just easy to copy, paste to other places. What you need is good knowledge of the system. You need to know what went wrong in the past, what functions were lost and now need to be restored, and then how can we restore these functions using nature-based solutions. And to do so, well, looking at what went wrong, in an estuary, you have an important interplay between the geomorphology, the habitats, and the hydrodynamics and the ecology. And in the Schelde estuary, the geomorphology or the habitats, they changed dramatically throughout history. This map shows you the estuary some 2,000 years ago. Everything green is tidal marshes and tidal flats. And the thin red line is the actual boundary of the estuary. So you see during the past centuries, due to embankments and later on to dredging, the estuary changed completely. This is how it looks now in the mouth area. Nearly everything is embanked. And then later on, we have the dredging, and dredging is deepening the fairway. But at some locations, the fairway, the depth has been doubled. So it has consequences. These changes changed the hydrodynamics, and it's obvious if you look at this graph. This graph shows you tidal characteristics, and on the left-hand side, on the left axis, you see the tidal range, and on the x-axis, the different locations along the estuary, and then you see for different time periods that there is an increase in this tidal range, and moreover, the highest tidal range can be found now more inland. This, of course, these changes in hydrodynamics, they will have their impact. But it's not only the not only the geomorphology that is changing the hydrodynamics, also in the basin of the Schelde, so the catchment, important changes have been made. And these changes in the basin, I can easily demonstrate it just looking at the map. What is an estuary? An estuary is a place where you have water coming from the sea, but also fresh water coming from the catchments. And every yellow arrow in this map is a tributary river discharging fresh water into the estuary. But the Schelde estuary, and it's the same for the Seine estuary, I guess, but it is situated in an area with a lot of canals. We have the biggest density of canals in the Schelde catchment. And all these canals, they need water. They need to be fed with water. And where's the water coming from? Well, from the catchment of our rivers, and in this case of the Schelde River. And if we look at the tributary with a red cross, it's the Durme tributary. Nearly all the freshwater discharge is deviated to feed canals, so we have tributary receiving nearly no freshwater input anymore. And the Schelde itself, the main course of the Schelde, well, only 39% of the original discharge is ending up in the estuary. So this has an impact on distribution of salinity, on residence time, and on suspended matter, and so on. So all these changes change the hydrodynamics, and the hydrodynamics on its turn will again change the geomorphology. Now, luckily, our marshes won't drown with rising tides because we have a lot of sedimentation, but the increased tides cause increased currents, causing lateral erosion, more turbidity, coastal squeeze, and the altered tides, altered discharge, causes tidal asymmetry, tidal pumping, and sedimentation. And some tributaries, some parts of the estuary completely silted up. So, and on top of that, you have ecology and pollution. So this all plays a role. And if you want to change something, you have to think as of the whole estuary. You can't just start changing hydrodynamics without influencing the other things. And if this would not be enough, we have climate change resulting in sea level rise, but also in more periods of droughts, and with heavy rainfall, peak discharges. Now, what can we do to change this? Well, habitat restoration, do some changes in the basin, or nature conservation. Now, I'm not going to talk a lot about changes in the basin, although they can be very important for the estuary. I only give one example. If you have buffering strips on arable land, like here on the picture, you can buffer water, but you also at the same time buffer nutrients and sediments, changing the discharge and changing the loads coming into your estuary. But back to the estuary, what can you do in the estuary, or what have we been doing in the Schelde estuary? Well, we had an estuary where we had a loss of ecosystem functions because we lost a lot of structures. And if we want to go back to the pristine situation, well, that is impossible. You can't go back because the space has been used for other things. So what we now try to do with the Sigma plan is looking for a sustainable solution. We want to restore functions, and we are looking at solutions for the actual needs of the estuary with its current functions. So I don't know if there are questions about this introduction. If not, I will continue with the second part. So how did we derive what kind of protection we need? How far should protection go? How much nature do we need? And what I'm going to present now is to a large extent based on the research I did with my colleague Stefan van Damme, who unfortunately left our research group. So we defined goals for several ecosystem services. So what we need to do is identify the amount of ecosystem services that we need, that are wanted to get a healthy estuary, and then work out the surface of habitats and the quality of these habitats that you need to deliver this amount of ecosystem services. And once you've done that, you have to translate this into then practical measures to create these habitats and this habitat quality on the field. We did that in 2004 for the Schelde estuary, and we made conservation objectives based on this philosophy. And I'm now going to show you how we derived these goals for carrying capacity for birds. We did it for other things as well, of course, but I'm only focusing now on the birds, on the wading birds that come here foraging on our tidal flats. So what we had to do is derive the surface needed to sustain the bird population and derive the required quality. How did we do that? Well, we looked into literature and we found out that there is a clear correlation between the number of foraging birds, of birds you can have in your estuary, and the availability of food. Not just the availability of food, but the product of the macrobenthos biomass with the surface of intertidal flats. So on this graph, you can see that correlation we found. On the x-axis is the product of B, is the biomass, times A, the surface of intertidal flats, and that is correlated with the number of birds. But this benthic biomass, here you can see some pictures of the benthic biomass, that biomass itself is correlated with the system primary production. And the system primary production, that is the algae that grow in your system. And when we look at the Scheldt estuary, but it could be any estuary, and you look at the carrying capacity for birds, so you're interested in this product of A times B, of surface times biomass, in fact, biomass density. And if you look on the left-hand side, you see the pristine situation, so a very long time ago, when there was little input of nutrients, nitrogen, N and P phosphorus coming from the catchments, and there was a lot of space, so you had a lot of tidal flats that were, you could say, low productive. But because you had a lot of tidal flats, there was still enough carrying capacity to have many birds in your estuary. What we have in the actual situation, and actual in this case means 2003, 2004, when we made these calculations for the Sigma plan and the conservation objectives. Well, what we had in those days is a very limited amount of space. A was small, but B, the density of biomass was very high because there was a high load of nutrients coming into the estuary. We use this into this formula where B initially, a BI times AI, the initial surface, in a past scenario where that product should now be compared to a current product of biomass and surface, where you can split up the surface in the current surface, and then the extra surface we need to have the same product, to have the same carrying capacity for birds. This is a bit a complicated scheme, but yeah, this is the way how we dealt with it. So you have this product, and the little index I stands for the initial biomass and the initial surface in a pristine situation. But to estimate this biomass in the pristine situation, we had to look at the primary production because it's correlated in a pristine situation and in a current situation. And it became quickly obvious that we should not do comparison with a pristine reference. We can't go back to an estuary without human interference. So we had to look at a reference where the situation was still good, but with a limited space. And we see, well, we can increase the primary production. If you increase primary production, then you have more benthic production, and then you don't need that much space. So with higher emissions, we can have more production on a limited space. And now the question is, what scenario is still acceptable? You cannot increase your emissions too much because obviously if there is too much emissions, too much nutrients, you will get a collapse of the system. You will have too much algal blooms, wrong algal blooms that will cause oxygen problems, and you get a decrease in diversity, in biodiversity. So we did some analysis, some modeling, and we found out that the 1950s, and we call it our pre-collapse scenario, is a scenario where we have increased nutrients, but the water quality was still good enough to sustain high biodiversity. And in those days, we had many birds, and we selected that one as a reference scenario. And now we went looking, how can we have the same carrying capacity for birds as the B times A calculation for the 1950 scenario. So we went calculating. So we took primary production from the 1950s to get a biomass, a density estimate for the 1950s, that multiplied with the surface of that period, and then seeing how it corresponds to the current surface we have future primary production, when water quality will be a lot better. And then you can derive what extra surface is required to have the same carrying capacity. And these calculations we did, so we derived the surface needed to sustain the bird population with future water quality. In future water quality, the loads will be a lot less, so we will need more space than we have now to achieve the same carrying capacity. And with our calculations, just for mudflat surface, we came out that we needed 500 hectares more than in the situation of 2003. But that's not all. There is also the need for a certain quality. If you have the surface of the tidal flats, the benthic biomass will only be there if the primary production is good. So what is needed for a good primary production? And primary production, that's the growth of algae. And what do algae need? Well, they need nutrients. But nutrients, we have plenty of nutrients. They need light, and then they also need temperature, residence time, and so on. But there is one big drawback. Not all algae are wanted. Diatoms are the basis of the food chain, and green algae, well, they are not preferred as a food source. Light is also very important, and I will first show you something about light. So phytoplankton, the algae, they need light to grow. And the light can only penetrate in the top layer of our estuary. This picture here, this schematic overview, gives you a cross-section of the estuary. And you see in the top layer, it's brighter, the sunlight can get through. So there, algae can grow. But deeper down in the estuary, the water gets dark. And the zone where light is still penetrating is called the photic depth or the photic zone, and it is depending on the estuary's turbidity. The deeper zone, there it's dark, primary production is not possible there, but the magnitude of this zone is very important. If algae are in the top layer, where there is primary production, they will grow, but due to the mixing in an estuary, these algae will come in the deeper layers, and in these deeper layers, they don't grow. They just wait until they are back in the top layer. And the larger these deeper zones are, or in other words, the larger or the bigger the mixing depth is, the longer an algae will stay in the dark. And so this ratio of photic depth, the photic zone, and the mixing depth or the mixing zone is very important. If the mixing zone is very large, algae will stay for a very long time in the dark. If the photic depth is very small, they only have a limited chance to be in a space where there is enough light. So these two parameters are crucially important. And we see that they have been changing in our estuary. I'm not going into detail any further, because in 2003 and 2004, when we did the calculations for the conservation objectives, we assumed that in the estuary, the photic depth would not change dramatically and the mixing depth neither. Now we know better, and we've witnessed that the photic depth changed dramatically. And so when we revise the Sigma plan in future, we will be focusing more on photic depth as well. So the photic depth, it changed, but also the mixing depth changed. If you deepen the fairway, if you have less or you create new shallow zones, then you also have an influence on this mixing depth. But I told you about the algae, that not all algae are wanted. So algae need light. You have to make sure that there is light. They also need nutrients, and then they can grow. And green algae are less wanted as a food source. They only need nitrogen and phosphorus. While diatoms, they form the basis of the estuarine food chain. They need, besides nitrogen and phosphorus, also silica, dissolved silica. They need it to build up their little skeleton. They have a skeleton, and this is a a picture of Cyclotella scaldensis. I just showed this one because we are proud that we have a diatom that is named after the Schelde. Scaldensis is the Latin name for Schelde. Now these diatoms, they need silica, and phosphorus and nitrogen, there is plenty of them coming from the catchment, but silica is not delivered in big quantities within the catchment. So what happens if there is a lot of nitrogen and phosphorus? The algae start growing until the silica is getting depleted. And when that happens, we see that diatoms can't continue to grow. And then the green algae, they have no more competitors. And so they can start taking over. And after a while, we have lots and lots of green algae. These green algae are less wanted as a food source, so they are not eaten as often. So they just build up biomass, and then when this biomass dies or is consuming oxygen during the night, you get oxygen problems. Or you get, as often seen, foam on the beach, as shown here in this picture. So how can we solve this problem using nature-based solutions? How can you increase silica and maybe decrease nitrogen and phosphorus? Well, for nitrogen and phosphorus, we should mainly look at the catchment, water purification, using less fertilizers, buffer strips, and so on. But within the estuary, you can also do something, and that is tidal marshes. And it's one of the earliest researches we did in the Schelde in 1997 already, that we saw that if you look at a marsh and make mass balances of what is flowing in and flowing out, then you see that silica is flowing out of a marsh every tidal cycle, while nitrogen and phosphorus are being taken up. So marshes act as a source for silica and the sink for nitrogen and phosphorus. Based on this, we could calculate the additional marsh surface that was needed to avoid silica depletion in the estuary. You could also try to remove nitrogen and phosphorus, but we quickly saw that you need a lot of space to remove all the excess nitrogen. But if you want to deliver silica, that is feasible by restoring tidal marshes. And so we made conservation objectives formulated as the required area of several habitat types, the required conditions concerning water quality, concerning water quantity, and so on. And we also included clear spatial aspects. For some services, it doesn't matter if you have many small pieces of nature, but for other services, it does make a difference if it's many small parts or one big marsh. So all these things were taken into account. All services have been added, have been combined, and then we came up with these numbers, the total extra surface needed in the Schelde to achieve a healthy ecosystem. For tidal brackish marshes and flats, we needed 740 hectares. And for tidal freshwater habitats, it's on average 1,500 hectares additional service. So there is also a spatial distribution. It matters where you create it. If you would all create these extra surface in the freshwater part or close to the border, it makes a difference. And this is how it was turned into real plans. This is a map of the projects within the Sigma plan. Within dark green, the existing marshes in 2003. And then in pale green, what should be added by 2030. And we can say that with the Sigma plan, there is some delay. We're almost halfway. And by 2030, probably not everything will be realized, but we will be hopefully close to this 1,500 hectares of additional surface. Now, how do we restore tidal nature? There are several ways. And one way to restore tidal nature is managed realignment. you just remove the dike and give back the space to the estuary. But in the Schelde, we have the special invention, you could call it, where we combine a flood control area with tidal marsh restoration. And how that is done is illustrated in the following slides of the Lippenbroek pilot project. This is an aerial picture of the Lippenbroek pilot project. It's a flood control area. And for a flood control area, you need an overflow dike indicated with a blue arrow. So when there is storm surge in the estuary, water will just flow over the levee, over the dike into the area. But for nature restoration, you need daily exchange of water with the estuary. And for that reason, there is an inlet construction with a yellow arrow and an outlet construction with a pink arrow. So there's water flowing in and out on a daily basis, but that's a limited amount of water. And there is flowing a lot of water in the site over the dike when there is a storm surge. Now the system of in and outlet, we call it controlled reduced tide, or CRT. And this is Lippenbroek seen from the polder side when the water is flowing in through this inlet construction during a spring tide. Now, why did we invent this system with a controlled reduced tide when there is also the option for managed realignment? Well, to a large extent, it has to do with the site's elevation. And I will compare both techniques. On the left-hand side, you see the managed realignment. On the right-hand side, you see the controlled reduced tide as shown here for Lippenbroek. Well, on the left-hand side, the managed realignment, it's a site usually with a high elevation that has not been embanked for such a long period. That is suitable for managed realignment. While on the right-hand side, you have an area embanked with a low elevation, less suitable for managed realignment, because if it is high tide and you would remove the levee, in a managed realignment site on the left-hand side, the site is flooded with a thin layer of water, as normal marshes should be flooded. While if you would remove the levee completely, in the example on the right-hand side, you see that the site would be flooded with meters of water, and that's not an ideal starting point for managed realignment, because you would end up with lots of mud, and it would take maybe decades before you have marsh development. So what is the solution? Solution is adapting the tide to the elevation of the area, using a high inlet that starts flowing in when it's high tide, combined with a low outlet construction. And this scheme can be combined easily with a flood control area. So if you have a flood control area, usually they have a very low elevation. You can build this inlet construction in the dike and an outlet construction to have this limited exchange of water, creating a controlled reduced tide. Now in literature, you can also find something called regulated tidal exchange, or RTE, that is used sometimes in the United Kingdom, and in Germany there are also examples of that, and they use one culvert, so one sluice, one hole in the dike for in and outflow. It is cheaper, but it also causes a reduction of water levels, but it reduces the spring tide, neap tide variation. Every tide, almost the same amount of water is flowing in and out, whilst in the controlled reduced tide, you have a high inlet, low outflow, and you have a reduction of water levels, but no reduction of the difference between a spring tide and a neap tide. Because during the spring tide, a lot of water will flow in. During the neap tide, nearly no water will flow in, because the water level in the estuary will not reach, or will barely reach, the level of the inlet construction. And so what happens if you build that? In this little animation, you can see it. Twice a day, water will flow in. During the neap tide, it's a little bit. During the spring tide, it's a bit more. And every tide, it flows back to the estuary. Now, this is all nice in theory. So we went checking it in Lippenbroek. It's a 10-hectare experimental site. And the main question now is, can a CRT fulfill equal functions as a natural marsh? Does it work? And well, we have to say it works. If we here look at the results for the tide, in this graph, the upper curves, they give you in blue lines the tidal range within the estuary itself, and the dashed green line is the natural marsh elevation. Below you see the curve in Lippenbroek and the Lippenbroek polder elevation, and what you see is there is a reduction by 3 meters of the high water level, but the difference in water height between a spring tide and a neap tide remains the same. So there is no reduction of the spring tide neap tide variation, assuring that we have a huge range in flooding frequencies, and that's providing us a healthy, diverse ecosystem. Now for water quality, I told you that we need to deliver silica, and that's one of the reasons why we restore tidal marshes, to have more silica in the estuary, to have a healthy diatom population, to sustain our food chain, the estuarine food chain. So we went checking the water quality, doing measurements, lots of measurements during day and night. And one of the first things we discovered is, well, these areas, they bring a lot of oxygen in the water. Oxygen deficiency will no longer be a problem in CRT areas. During inflow, the sluices themselves, they aerate the water a lot. There's a lot of turbulence. And during outflow, when the water stayed for quite some hours in the area, we see that the oxygen levels keep on increasing, and during outflow, there is supersaturated water. So this is really bringing oxygen in our estuary. We also see that these areas, they remove nitrogen. They are a sink for nitrogen, here expressed as total dissolved inorganic nitrogen. And every dot is the result of a tidal campaign where we measured a full tidal campaign, the inflow and outflow of water, and then made up the balance. And we see, well, after many, many campaigns, that there is always removal of nitrogen. So the site is always a sink for nitrogen, but it seems that there is a decreasing trend, that the amount of nitrogen being removed by Lippenbroek is going down. Is this true? Is there really a decreasing trend? Well, yes, there is a decreasing trend, but that is due to improved water quality. When the nitrogen concentration in the estuary is going down, then of course the removal efficiency, the amount of nitrogen that can be removed by tidal marshes, is also going down. That's when you calculate with ecosystem services. A service is very important when there is high need for it. When water quality improves, the need for the service nitrogen removal goes down, and so the efficiency of a marsh is going down. Well, but there is no indication that the functionality of Lippenbroek is going down. It's just the estuary that is improving. And now, most importantly, for dissolved nitrogen, because that was a major goal of these areas, do these areas deliver dissolved silica? And this is also for many years where we have been making mass balances, and then we saw that there is very often import of silica and not always export, especially in the first years. But luckily, here we see that there is a trend towards more and more exports. And this is also due to changes in the estuary? No, in this case, not. Here it is really the site that needed some time to develop. The delivery of dissolved silica is a process that is taking place within the soil. And when we created Lippenbroek, before that it was agriculture. It was compacted polder clay, and apparently it takes several years to build up an estuarine soil that can deliver the service of silica delivery. So we see that in the first years, there was not a lot of export, but now, in the more recent years, the site is really exporting silica, preventing unwanted shifts from diatoms into green algae. And with that, we had enough evidence to say, well, it works, these controlled reduced tidal areas, and we are ready for large-scale implementation. And large-scale implementation, this is the example of the controlled reduced tidal area in Kruibeke. It was built during several decades, was a huge work. And on the left-hand side, you can see the construction of an inlet and an outlet sluice. Look at the size of the large trucks that are driving around there. It is really huge. And on the right-hand side, you can see the first official inauguration of this sluice in 2017, when the water flew in for the first time. And now it's working for more than 5 years, nearly 6 years. It's working perfectly, developing into a really nice, beautiful tidal marsh. And this is also building with nature. So we created the right conditions, in this case, creating the right tidal conditions with hard infrastructure, concrete. These sluices is a lot of engineering works, but once that is done and the conditions are created, it's up to nature to do the job, to purify the water, to deliver silica, to create habitat for species, for birds, and so on. So with this, I want to finish my presentation and give the word to Joris.
Alors, merci Tom pour ce slide sur le projet de Sigma. Je ne sais pas s'il y a déjà des questions sur la seconde partie des slides. Sinon, ouais,
Moi,
quelque chose, mais ouais, Manuel.
Moi, peut-être, j'ai une question concernant la disposition spatiale des secteurs qui ont été identifiés au départ dans le Sigma Plan. Comment elle a été faite? Elle était basée seulement sur des besoins écologiques ou il y a eu aussi une réflexion qui intégrait aussi les usages quelque part dès le départ pour viser des secteurs dans lesquels la faisabilité était quand même élevée? Do you want me to translate? No, it's fine.
I think I understood the question. So you mean the spatial distribution of the sites along the estuary, how we decided what should be done where? Well, the first driver was the safety aspect, and maybe Joris will go into detail about that. But some sites along the estuary had really good properties to be a flood control area. Low elevation, long stretch along the estuary, so that they could function as a flood control area. And then within these flood control areas, from nature point of view, we've been looking what is the best function we can give additionally to this flood control area. Not all flood control areas are turned into tidal nature. Some flood control areas have non-tidal nature. They are a wetland, grassland specifically for birds. Some are forests. Even some flood control areas still have an agricultural function. It just then depended on the site's characteristics and the local need for a certain service.
Donc, then it's after that you will try to manage how to implement the projects, like in terms of feasibility. If there was the agriculture inside, you manage how to place them.
Yes, well, That was sometimes a difficult process, but one of the lucky things we had is time. The Sigma plan, it took a lot of time to construct it. So there was a lot of time to interact with farmers, so that they also had a lot of time to change their way of farming. Some farmers just got compensated. Other farmers were giving contracts to do maintenance within these sites. But yeah, to change a farming company, it takes time. They have their livestock, they have their way of doing things, and you cannot say all of a sudden, tomorrow you have to change it. No, it doesn't work. But luckily, from the decision to the creation of a flood control area, it can take 10, 15 years. First, the land needs to be expropriated. Then the dikes need to be built. And in all that period, farmers, they could continue doing the maintenance, because if you don't do anything and you just kick out a farmer, then that's not good. So farmers kept on farming while construction works were ongoing, especially in the larger sites like Kruibeke. It's a site of 600 hectares. During all that period, farmers have been, during the entire construction phase, farmers have been involved. Sometimes parts of the polder became grassland for meadow birds. Someone had to create the grassland and get grassland in good condition. You can ask a farmer to do that. In the original plan, the Agency for Nature and Forestry had foreseen to put wild horses in there, or some wild cows. But then with discussion with farmers, they said, what is the goal? Is the wild cow or the wild horse the goal, or is the bird the goal? And I would say, yeah, the bird is the goal. And farmers, they said, but we can make sure that the grass is in perfect condition for the birds. We are farmers. We know how to grow grass. We also know how to maintain a meadow in suitable conditions. And so in that way, farmers were involved also for maintaining the grass on the dikes. And of course, there's not as much work for farmers as there used to be, but because of there was the long time period, 10 to 15 years, other farmers could change their way of farming.
Romaric, tu avais une question?
Yes. Many thanks, Tom, for your presentation. It's really impressive, the work that was done in the skills. I have many questions, but I listed them, so I will ask them later. I will just ask one. I was wondering, you perfectly show the interest in RCT to lower the nutrients in the estuary with some budget calculated. I was wondering if you tried, or if it's true to try to extrapolate it to the area we need to develop so that we would lower the mass of nitrates or nitrogen in the estuary so that it becomes better environment. So the question for nutrients is also true for silica, but I took the nitrogen. I mean, are you able to multiply by the area and say this is what we need?
Yes, and we did in 2005. We also looked how much space would we need to remove the excess of nitrogen. The amount of space needed was, I don't know by head, but was
Too much.
maybe tenfold of the amount of marshes that we are creating now. So there is just way too much nitrogen to purify it using tidal marshes. Nitrogen removal is, we think, a problem of the catchment. There should not be that much nitrogen in the water. It's better to do more water purification, wastewater treatment plants, and have more restrictions for agriculture. That is way cheaper than trying to solve that problem by building marshes. But for silica, it's different because farmers, they don't put silica as a fertilizer in such quantity on the field. And there it is possible by creating more marshes to raise the silica level to have again the correct ratio between nitrogen and silica, assuming that the nitrogen levels would go down. So what we calculated is we need, I think it was about 1,000 hectares of tidal marsh for silica delivery. And then we have a good silica nitrogen balance when the nitrogen levels go down to a level that is about what the Water Framework Directive is asking us. And that should be achieved soon. It is not the case in the estuary, but we will achieve that one day.
Many thanks for your answer. I think Gabriel also has a question. I can pass.
Et vous donner la parole, Gabriel. Si vous pouviez essayer de poser votre question en français d'abord, histoire que si elle n'est pas bien comprise, répétez-la en anglais, il n'y a pas de souci. Mais au moins, comme ça, on essaie d'inclure tout le monde le plus possible. Merci.
Entendu. Merci beaucoup pour cette présentation. Donc, moi, ma question, c'était une question sur les autres paramètres de qualité, les herbicides et les insecticides. Parce qu'en fait, je comprends que donc, dans les paramètres de croissance de la production primaire, vous avez bien regardé qu'est-ce qu'il y avait besoin en azote, en phosphore, mais est-ce qu'il n'y a pas des inhibiteurs de croissance de la production primaire? Est-ce qu'il n'y a pas des inhibiteurs des invertébrés?
Oui, probablement. So we know that there are pesticides in the water. As far as we know, the pesticides are not hampering the algal blooms, but they might have impact on the zooplankton. Now, with the Sigma plan, we did not focus on pesticides, also not on heavy metals or PCBs or PFAS, because as an estuarine manager, you can't solve the problem of pesticides by creating nature. You can do something about nutrients because nutrients can be converted within your system. And the Schelde, as a bioreactor, is doing some self-purification. But the problem of pesticides, of heavy metals, is a problem of the catchment. And so there it should be tackled by stricter regulations, by more water purification plants, and so on. It's not something that an estuarine manager can solve, so we cannot give advice to an estuarine manager to do anything about it. What we did saw is that in the period before the year 2000, that the water quality was that bad that even the high ammonium concentrations slowed down the algal growth. We had sometimes anoxia or hypoxia, high ammonia concentrations, and that hampered algal blooms. So by solving that problem, by adding more oxygen to the water, so that all ammonia is now oxidized into nitrate, we don't have the ammonia toxicity anymore. So that's a toxicity problem we can solve within the estuary, but not the other pollutants.
We don't hear you, Mathieu. If you want to talk, we can't hear muted. Ton micro est coupé. Pardon.
Donc, vous devriez m'entendre. C'est bon? Vas-y, Romaric, je pense que c'est le moment de poser ta question suite à la présentation de Tom. C'est le bon moment, donc je t'en prie, on va enchaîner après.
En fait, Joris a répondu dans le chat en disant qu'il allait y répondre plus tard.
Oui.
Ah, je viens de le voir, pardon, ok. Eh bien...
Donc c'est une belle transition, sauf s'il y a d'autres questions, on peut le laisser démarrer sa présentation et puis on y reviendra après. Sauf s'il y a
bien.
d'autres commentaires.
Eh bien, très bien. Bah, Romaric, tu es un très bon modérateur aussi. Joris, c'est la parole.
Merci. Alors, de ma part aussi, bonjour à tous, bonjour à toutes. Je m'appelle Joris Vanlede, je suis affilié au Flanders Hydraulics à Anvers, en Belgique. Et alors, merci de nouveau pour nous donner l'opportunité de partager nos connaissances sur le plan Sigma d'une part et le projet LifeSpark d'autre part. Alors, si vous avez des questions pendant ma présentation, n'hésitez pas de m'interrompre, poser vos questions dans le chat. Je vais essayer de répondre en français, mais le reste de la présentation, je l'ai préparé en anglais, comme Tom a fait. Maintenant, je vais essayer de partager l'écran. Alors, now I have to switch to English. So I'll talk first about the Sigma plan, again, as like a broader framework. I come at this from a particular EU-funded project, which is called LifeSpark, which is tied to the Sigma plan. So that's why I'll start with the broader Sigma plan first, and then I'll go a bit more in detail in the LifeSpark project. And I'll use the opportunity to highlight two areas. We already saw a bit of examples of Kruijbeke, Basel, Ruppelmonde in Tom's slide deck, so I'll add a bit of information there. And when I talk about when I'll talk about the LifeSpark project, I'll also use Walswijn, Grootschoor, a different area which is part of the LifeSpark project, to illustrate some of these general principles. So first, about the Sigma plan. So this will overlap a bit with Tom, so I'll skip a few things, but I'll highlight some details that haven't been mentioned yet. As Tom mentioned, the impetus of the Sigma plan was the flooding of January 76, so that gave rise to the Sigma plan in 77. You can see here the Sigma, the S of Sigma stands for Scheldt estuary, and the Sigma, the fact that we use the Greek alphabet, is a nod and a wink to the Netherlands, basically, because they started with the Delta plan, which is another Greek letter. I'll talk a bit from, I work in an hydraulic institute, so I'll take that perspective a bit. And one of the things that strikes me, one of the things interesting to note, let's say, is that the original Sigma plan started, it was much influenced by the Delta plan. It started from a safety against flooding against an extreme event. So in that plan, they took a 1 in 10,000 years storm event, and then they designed the plan to protect the estuary against that particular event. Now, regarding the question of Romaric, I'll address partners a few times in the slide deck. So the Sigma plan itself was the responsible for the Sigma plan is the manager of the estuary, which is now called the Vlaamse Waterweg. The name of the agency has changed over time, but it's now the Vlaamse Waterweg. And as Tom mentioned, the plan of 77 was updated in 2005. And at that point, very interestingly to me at least, is that from a unilateral approach against safety against flooding, it became more a multifunctional approach. And at that point, a second party gets involved, which is, I think, already mentioned also in Tom's slide deck, which is Agentschap Natuur en Bos. In English would be Agency for Nature and Forestry. Because when the original Sigma plan had a sole focus on safety against flooding, the updated Sigma plan broadened the scope a bit to include ecological restoration, to include an economical dimension, and to also include recreation. A second bit that changed is more or less at the same time. There was also a long-term vision of the Scheldt estuary, which was developed, and that isn't directly tied to the Sigma plan, but it's you could see it as a plan that was developed by the region of Flanders, which is like the northern region in Belgium, and the Netherlands as a country, and where they say, look, the Scheldt It has to protect the people who live there. Safety against flooding is an aspect of the long-term vision, but just as well, ecology is a second pillar, and the third pillar is accessibility. And that is because the port of Antwerp is, well, it needs access via the Western Scheldt. So through the Netherlands, it needs access to the North Sea. So the long-term vision was really based on how can we develop a long-term vision of the Scheldt that enables those three pillars at the same time. But enough about long-term vision. I'll focus on the Sigma plan, which has a slightly narrower scope than the long-term vision. Here, I think Tom tackled this already. Is interesting enough, the choice during the updated Sigma plan, they took like a societal cost-benefit approach. So it's really an economical type of reasoning that enabled us to. So there were, as you can see here, there were 5 options on the table, let's say, and then they basically quantified everything economically. So even the ecological benefits you can see here was quantified in euros. Or in, I think, million Belgian francs at that point. And the choice was really based on what is the fastest payback period. So it narrowed it down into an economical framework, let's say, to make the choice, which objectifies the discussion a bit. And if you want to do that, and that's an element that I want to add to the story that Tom already said, and also where my institute got involved a bit more heavily, is we took, when I told you earlier that the 1970 plan was, from the Dutch example, was really how can we protect the estuary against a 1 in 10,000, so very rare storm. When we updated the plan, we took what we call a risk approach. So rather than focusing on one extreme event, we took an ensemble of multiple events, like a yearly event, all the way up to a 1 in 10,000 years event. So we did numerical simulations. We defined those types of events statistically, and then we calculated that with numerical models, like what would happen if this type of storm would hit the estuary. And then we went all the way to flooding calculations. Which enabled us, in combination with land use, in combination with damage functions that say, if a certain land use gets flooded for this many centimeters for this much time, you get a reduction in value of this many percentage. So these kind of cost functions is really looking under the hood of the societal cost benefit analysis. This damage function informs the damage expressed in euros of a certain event, and then the risk is basically you sum all these different events weighed by their probability, and you end up with a result again in euros. So that's how this fit into the societal cost benefit approach. So you can see that moves a bit away from this protection again 1 in 10,000 years event into more of a risk approach. And the interesting consequence of this is illustrated in these 2 graphs, is that it's intuitive to understand that there's a difference between, but it depends a bit on the value of what you're protecting. Like suppose that there's a city or a village which lies behind the dike, the cost if that would flood would be much higher than if this would be agricultural land. There is a cost, but it's lower. And when you take a risk approach, you kind of integrate this and you can optimize and you take into account the fact that you have different values of land use over the estuary. And so that was the update in 2005. Right now we're in what we call internally Sigma 3.0. It's currently in a strategic exploration phase, and we're basically preparing ourselves for the situation post 2050. For the situation after the Sigma plan would be, the updated Sigma plan would be totally rolled out, totally executed. And we can see what can we do after this. So this is again a multidisciplinary approach. So University of Antwerp is involved, the ecological team of Tom is involved. The Research Institute of Nature and Forestry is also involved, and Flanders Hydraulics is involved as hydraulic experts. First scenarios that we're talking about is there's some reserve areas that were identified within the updated Sigma plan but will not be developed. What would happen if we would then attach those areas to the estuary? What is the added benefit of them? The storm surge barrier that was mentioned in Tom's story that was not selected in the updated Sigma plan is again put on the table, like, does it make sense now? Because one of the main differences, as you know, is that in between the update of 2005 and now, in these 20 years, the Earth hasn't cooled, and plus climate science has evolved in these 20 years. So where the updated Sigma plan started with scenarios of sea level rise, they basically took into account 60 centimeters of sea level rise over 100 years. If you look at the latest IPCC reports that we took as a basis for Sigma 3.0, we can see that when they talk about 2100, you have the RCP 8.5 scenario that translated for the Scheldt, the order of magnitude is a meter of sea level rise, not 60 centimeters, but a meter. So that's already higher. And the estuary manager has added, just in terms of robustness, they've added a second, more extreme scenario of, they ask us to, any idea that you have, also calculate this to up to 2 meters of sea level rise. So the sea level rise scenarios are also updated in between the updated Sigma plan and Sigma 3.0 that we're currently in. So actually the idea of this knowledge transfer was done during the site visit of the IUCN conference, where I met Manuel and Mathieu. That was in 24, and there we took the opportunity we did a site visit to both Kruibeke and Walswijn. Those are also the two areas that I'll explain more in this slide deck. So those are the two areas where they're located in the Scheldt. And so the polders of Kruibeke, as Tom already mentioned, that's the biggest flood control area that we have in Flanders. It's quite sizable, so it's about 600 hectares. Since 21, also recognized as a nature reserves. And it's a project with a long history. So this is the earliest report that I found in our archives that's way before my time. Colleagues were already thinking and modeling the effect of attaching such a big area to the Scheldt, what the effect, for instance, hydraulically would be. This is, I think it's kind of double with what Tom said. So the polder of Kruibeke, but I'll repeat it again, because this is, I think, quite unique in Flanders, is this combination of, you can have a flood control area which would flood during storms, and you can combine it with a controlled reduced tide. You can see that here in this little, that's very little, but the flood control area would be overflow over a dike and then outflow through an outlet culvert, whereas a controlled reduced tide, it really enables you to have a controlled reduced tide, as the name suggests, in the area every tide. So here you can see these sketches again, but I think the principle was already clearly explained by Tom. You can see Tom had an aerial picture of the opening of the area of Kruibeke, Basel, Ruppelmonde. You can see there's quite a lot of people, and that's up to this date. We can see that it's quite dramatic. It was a very big inflow structure, so I'm an engineer. From an engineering perspective, I find these things very interesting. But also during spring tide, for instance, there's quite some force, some power, hydraulically speaking, then, of water flowing into the area. It's even nicknamed by the tourism board of Kruibeke as the waterfalls of Kruibeke, and because it has kind of a recreational, touristic type value, we did a small effort within the LifeSpark project. Is we use the fact that we have at our lab, we have prediction of the tide in the Scheldt, so operational prediction of, we use meteo models as input. So we predict the tide in the North Sea, then we predict the tide in the Scheldt. So we can say a few days beforehand, we can already predict what the tide will be in the Scheldt, in the vicinity of the area. We know where the inlet sluices are. So we built kind of a website module where you could, if you want to see the area, it's quite possible that you want to visit it during an inflow event. And if you're not an expert, it might be hard to predict. So we made this a bit easier. So on this site, you can have a little calendar where you can see the main inflow events will be on these dates. Those are the spring tides typically. It will be on that hour. So you can plan your visit to the sluices. That's kind of this recreational touristic aspect. that wasn't part of the original plan, and it's also for us as hydraulic engineers kind of a learning curve, and was for me actually one of the nice things of the LifeSpark project is that because we have a lot of other partners involved, including communication bureaus, is that they make us attentive that there might be some societal benefit if you have the knowledge, if you can just make it more accessible. So we followed that example. Now, a part of Kruibeke-Basel-Rupelmonde is GOG, is flood control area, meaning there's an overflow dike. You can see here, this is 10 years of water levels in the Scheldt in a location pretty close to the flood control area. The red line here, that's the height of the overflow dike. You can see that there's a small bit of this water level distribution is higher than the overflow dike, as you would want, basically, because for instance, oh, sorry. This is a recent example in 22. This is the storm front of the storm, which had the name Corrie. Northwestern winds, that's typically the weak point of the Scheldt estuary. If you have a northwestern wind blowing, you kind of push North Sea water in the Scheldt, and that raises quite dramatically the water levels in the Scheldt, with 6 to 7 Beaufort. We also had the peak of wind also coincided with the high water, so that's like the perfect storm, so to speak. So KBR, or Kruibeke-Basel-Rupelmonde, was active, and this is how it looks. So this is really the overflow dike functioning. So that's intentional. So this is one of the events when KBR really functions as a flood control area, where it has a measurable impact. This is one of the reasons, is the safety aspect of this area. This will capture some of the water really during the bit of the high water peak, like the most dangerous bit in terms of flooding. That water is then captured in that area, and it has a real safety benefit. So that was about like a bit of information on the general framework of the Sigma project, and now I'll dive into the LifeSpark project. LIFE is, as you might know, is a European Union funding type program. Spark is the name of the project, so LifeSpark is the full title. And what we did together with the Vlaamse Waterweg is we wrote this proposal to basically get co-funding to develop 8 of the areas that were foreseen anyway within Sigma, to get co-funding of Europe. LIFE is not fully funded. It means that Europe will fund 60% of the total cost. That's the project structure. But it's always welcome to have an additional subsidy for these areas. So the intention is, I'll come back to that in a bit, is to reduce flood risk further. We express this as it will have an effect of 35 centimeters during a T1000 event. We are developing in total 428 hectares of tidal nature. It has 4 pillars. It's nature development, but again, multidisciplinary approach, as the updated Sigma plan also has. So it's nature development, it's safety, with translated into giving room back to the river. It's also knowledge sharing, so that's where this event comes in. This is part of the philosophy of the LifeSpark project, that's an important part of the European project. And we also have a pillar on building social support for these projects. Budget is 8.5 million, and the project runs more or less 4 months more till the end of August of 25. So here, the project partners are a bit broader than Sigma proper. So you can see here the Agentschap Natuur en Bos, so the Agency for Nature and Forestry, and the Vlaamse Waterweg, the manager of the Sea Scheldt. They're involved. They're main partners of Sigma. But you can see for this project, for the LifeSpark project, we extended this a bit. So we have Regionaal Landschap. They've now morphed into a nature park, but I'll come back to that later. And then I'm affiliated to 2 different entities, which is Flanders Hydraulics and the Eigen Flanders Hydraulics, where we were involved as hydraulic experts. So a bit on these 4 pillars of LifeSpark. So one is giving back room for the river. That's in the philosophy of Sigma. So that's building climate buffers. It's basically 5 depolderings and 3 flood-controlled areas with a controlled reduced tide. We know that concept now. These are the location of these areas within the Scheldt, but again, they're part of Sigma, so you can use the mental image of that Tom earlier showed with like the complete Sigma project. Is we have areas over the entire Sea Scheldt, and we just picked 8 of them to put into the LifeSpark project. And the project rationale that we used to sell this, so to speak, to Europe was the fact that you can see here this is the longitudinal axis of the Scheldt. So this would be the Dutch part, and this would be the Belgian part up to the end of this is there's a structure here. So this is the end of the tidal wave. We can see here the high water level, and it's well, you have a combination of what we call technically tidal amplification, because it's a funnel-shaped estuary. The tides get amplified, and then after a while the friction dominates, and then the tides get damped again. But what we see here, interestingly, all these different lines is averages of high water over 10-year periods. And I think Tom also had a similar image like this. You can see that the tidal amplitude, there's a bit of tidal amplitude increase already at the mouth, but you can see that within the estuary, due to morphological changes, this tidal amplitude has dramatically increased more. It's much more than at the mouth, and in the North Sea, there's a much bigger effect due to morphological changes in the estuary, which means that you constantly need to update. If you want to protect yourself against flooding, you constantly need to update your plans, because this is a dynamics that hasn't stopped yet and is still ongoing. And so within this safety rationale, what you see here is this is, again, a bit under the hood, is the way we do this is we have models of the Scheldt. In this case, this is a 1D model of the entire Scheldt from the mouth all the way till the tidal limit. And here we calculated a T1000 event, so a single event. And we can see here the highest level of the high waters over the entire estuary. So from mouth to the upstream end. In green would be when you complete the LifeSpark project. In gray would be without the LifeSpark project. The difference, here you can see this value of 35 centimeters. For this one particular event, the T1000 event, you would get a 35 centimeter benefit at this location. So we could prove, we did these calculations before the project started. This was part of our basically dossier that we submitted to Europe. We could prove already, like, this is a measurable effect that will have, that these 8 areas will have on safety against flooding in Flanders. The second pillar, so it's not just safety against flooding, it's also nature development. I mentioned this 428 hectares also, and part of the deliverable, one of the deliverables of LifeSpark was also to develop climate-proof nature management plans for all of these areas. The project rationale there is that we can show, based on measurements, is that there an historical loss of habitat in the sea Scheldt that we try to mitigate with these kinds of projects. And then the third pillar is knowledge sharing, where, well, this would be, you can see the Seine here mentioned, this is one of the ways that we fill this pillar in. Also the IUCN conference that we participated is also part of that pillar. And then a few more words on building social support. Within the LifeSpark project, we trained 90 ambassadors, which are typically people involved in tourism, recreation, think hotels, think horeca, think brasseries close to the Scheldt. There's quite a lot of cycling paths next to the Scheldt, so there is already some tourism. So we basically pull these people in, we inform them about the LifeSpark project so that they can basically tell this story to their clients. They can use it in their branding. We invested in an event. I'll give some details there later. And we also invested in developing what we call climate trails. It's kind of an educational purpose, that there are some designated paths with some lesson material that schools can use to visit these areas that we developed within LifeSpark. Now, I mentioned here earlier Regionaal Landschapsgelden Deurne as a project partner. They now morphed, or they lay at they co-founded basically what is called in Belgium a national park. National park is a quite recent idea within Flanders. So it's a Flemish, it's within the region of Flanders. It's a recognized geographically defined area of sufficient size with exceptional natural value. And it's again multidisciplinary. So it takes ecology into account, but just as well landscape. like the combination of you have an estuarine landscape. There's agriculture there. There's forestry there as well, and heritage. We have quite a rich heritage with castles next to the Scheldt, etc. So that total, that is the national park. So it has it has a focus on recreation, again, on tourism, and it was designated in 2 years ago in 23. And one of their selling points is, again, Tom also mentioned this, is that the Scheldt has quite a unique tidal nature. I think even unique within Europe is that the Scheldt is a microtidal estuary, but it's so microtidal that you have a freshwater part in the upstream bit that is also tidally influenced, and that detail is actually very rare in Europe. So it gives you unique ecological value, and that was part of the reasoning why Seine-Aval was selected to be, because there were 10 candidates and only 4 were selected. That became one of the national parks. And the other element that I mentioned was this event. So within Lijspark we did, I think, 2 Hoogtij events, which is again building societal network, building acceptance, getting our story out. And that is now morphed into the Stroom Festival. So now we have support of Festival van Vlaanderen, which is one of the cultural powerhouses, I would say, in terms of classical music in Flanders, and they connected with Stroom Festival. So it's a cultural festival which is now going to be organized, I think, in July for the 4th time. So you can see here it's different. It's a musical festival, but then they try to play with this connection to nature again. So they will give performances close to the river. I went 2 years ago, which was it was very, very impressive, and it's quite unique to experience music in connection with nature or an estuary. It kind of it works very well. Within, I'll diverge a bit back closer to my area of expertise. Is I'll use Walswijn and Groot Schoor, which is an area developed within Lijspark, to explain some concepts a bit deeper. And what I wanted to use this as an example for is that I consider Sigma, it gives us as hydraulic engineers, it gives you like building blocks, like a couple of ideas that you can play around with. And Walswijn and Groot Schoor is, I think, a good example. It's kind of a Tom also used this word already. It's really a tailor-made solution. And you could see that very well in this area. It has a combination of part of it, the light green here, that was a depoldering that is called Groot Schoor. And then this area, Grote Wal, Kleine Wal, and Zwijn in dark green, there a CRT is managed. So you can combine different ideas, a depoldering and a flood control area with a control to reduce tides. These ideas can get combined. So if we start with the depoldering, that was a depoldering of 26 hectares, which is depoldered in 21. So we're now 25. So we can already see, so this is pre-depoldering, this is post-depoldering. This is, I think, just after these breaches have opened. And interestingly, so yeah, technically they lowered the dike so that the water can overflow. They breached it even on connecting to, they dug onset of creeks. So they gave nature a small push, and then the rest is basically nature development. At that point, the hands are off. And I hope this works. And I don't know whether the sound passes through. No, I have it in my ear. Then I'm gonna mute this. So those are some aerial pictures of the development of Groot Schoor. So you'll see the tidal breach, and well, the explanation is in Dutch, but it's saying here that nature development. So what we did is we deliver a creek onset. So that's an animation of the breach. We give it an onset. So we do initial creek development, but it's under dimensioned. So we know, like we know what the expected equilibrium dimensions are, but we don't dig all the way there. So we let nature basically do kind of the heavy lifting for us and the sediment transport for us. So here you can see, yeah, again, I'll let the images speak a bit for itself. And here we can see we have some aerial pictures. So this is just after breaching. I think maybe even one of the first flooding events. So you can see you have these dikes, and already, like this is a year later, you can see already creek patterns forming naturally. This is what you hope when you design such a project. You can't exactly predict exactly how these creek patterns will look like in the end. You can have an a priori idea about the general shape and the general characteristics, but that's basically fine. What would be your concern? And this is how it looks in winter. So the area is still in full development.
Joris, may I ask
Ouais.
a question?
Sure, Frédéric.
Une question. En fait, je me demandais, le fait d'avoir fait les brèches, est-ce que vous avez renforcé les digues en champs proches pour être sûr que ça s'augmente pas, ou est-ce qu'au contraire, vous laissez à la rigueur la nature, et est-ce que potentiellement la brèche peut s'agrandir et c'est pas un problème? Comment vous avez géré ça? Did you get it?
Yes, I understand. So from Tom, please fill in as necessary. As I understood it, even the breaches are also underdimensioned. So we let the breach will naturally widen up till an equilibrium section. So I don't think they're reinforced. Okay. Maybe Tom.
No,
they're not reinforced.
No, they're not reinforced. Well, if the dike itself has no longer a function, the dike it can erode, and sometimes we do want to remove the entire dike because it has no function, and it would be better to have nature instead of the dike. But yeah, there is a matter of cost, and that's the reason why often there's just a breach and not entire removal. Another reason why dikes are sometimes kept is for the navigation. When it's high tide and the dike is gone, some ships, they don't know where the fairway is. Well, professionals, boats, they know, but sometimes these hobbyists, they get lost.
Makes sense. Many thanks.
Yeah.
And maybe one thing that I want to add is that, as Tom mentioned, the dike itself, once it's designated as a flood control area, the dike itself, the skelt dike, the dike close to the skelt, doesn't have a safety function anymore. And that's why before the dike is breached, the first part of executing this project is building a secondary ring dike that takes over the safety function. So even if you breach it and you don't reinforce it, it would be perfectly fine if even the whole dike would erode, because the primary function has moved. So maybe a small question to Manuel or Mathieu is, I see some questions popping up in the chat, but I can't read them at this point. If one of them is if a clarification is needed in the chat, please interrupt me and then I'll address those. Otherwise, I would suggest that we take the questions that we recorded in the chat at the end of the presentation.
Oui, je pense que ça sera intéressant d'aborder ces questions un peu sur la gouvernance et sur la faisabilité des projets un peu à la fin, quand tu auras terminé ta présentation, je pense.
D'accord. D'accord, merci. Then the examples, the previous examples is on this part. That was the depoldering here of 26 hectares of Groot Schoor. And then we have this part, which is a controlled reduced tide. And here you can see that the controlled reduced tide is going to be in this particular area. It's again made to measure it. So we're going to do this with 2 in and outlet sluices. So that's like a higher cost. Why would you do that? That was studied, and typically the height of these areas that you depolder, it depends on how long they've been poldered, how long they've lost the connection to the skelt, as you can imagine. And you can see sometimes you could see in aerial images, some areas are significantly lower than others. And this was the event here, is that one of these areas is significantly lower than the other one. So in order to have the best possible nature development possible, it was best to split this area in 2 basically, and to make a controlled reduced tide with 2 inlet structures. So that again, this modularity and the fact that you can play around with this as building blocks in order to get these multiple finalities that we try to hit for each of these areas. So it wouldn't be having one big inlet and outlet sluice would not be favorable for the development of tidal nature in this area. And also, you can imagine that that's an element, part of controlled reduced tide, is it's not just nature, it also still retains its safety against flooding event. So the idea is that when a storm hits, these areas ideally are as low or are empty, so that they still have the full capacity to attract, to basically store water of the storm peak. And that was also the safety function was also better if we split this area in two. And this is a difference, an interesting difference for me, at least as a hydraulic engineer, between Kruibeke, Basel, Ruppemünde and this more recent area of Waalswijn is you could see in the aerial image of Tom is that for KBR, Kruibeke, Basel, Ruppemünde, there's a separate inflow and outflow structure built, and later on we kind of played with the idea is can't we combine these two, and that's perfectly feasible. Is because you just need to make sure that your inlet is higher than your outlet, but you can stack them on top of each other, which is kind of, it makes economic sense. This is cheaper to build than what we did earlier at KBR, where we had two separate structures. So you can see that the inlet happens like this, then there's a return valve that is closed gravitationally, and that opens up during outflow if the water level in the Scheldt is low enough. So that's, I think, interesting to note in general about the concepts that we use within Sigma. It's totally gravitational flow. There are no pumps. It's gravitation playing. It kind of limits yourself in terms of, I mean, you could imagine if you have you could also think about an active structure. You could modulate this every 10 minutes with I know weirs and stuff like that. And we have another part of our knowledge transfer is a connection with the Waterdune project in the Netherlands, and there they chose such a very highly finely regulated active approach. But that's not that wasn't specifically a design choice within Sigma. All the areas are they don't have an active control, let's say. So what we can do is we can heighten this a bit by adding schotbalken, by adding like wooden beams to basically heighten the moment of inflow, to change the moment of inflow. But that's about it. And during extreme events, we can manually close this just to maintain the safety against flooding structure, or whether you want to maintain something. So, but that's it. There's no software that controls the tide in these areas. This is pure gravitation and passive culverts. And I think this is the last slide. This is how this combined structure looks like for Waalswijn.